Hi, this is Matt Roscoe with our fifth and final lecture in our course M573 Geometry for Teachers. So today I'd like to go over are how the three different perspectives of geometry that we've sort of built the course around come into play in problem solving, especially in geometric problem solving. So let's just review what the three different perspectives of geometry are that are taught in K-12 mathematics. Synthetic, analytic, and transformational geometry, and then talk about their role in problem solving. We'll do some examples, and then I want to do one last GeoGebra instruction on how you can help kids understand the problem solving process using technology. So the three geometries, remember that the teaching of geometry in K-12 mathematics can loosely be categorized or organized into three different perspectives in which mathematical objects are visualized. These perspectives are synthetic, analytic, and transformational geometry. So let's just review each one of those. Synthetic geometry, sometimes we call this axiomatic or pure geometry, is the study of shape using an axiomatic method that begins with a set of givens, usually called axioms or assumptions, and builds results, usually called theorems, using only the tools of logic and the tools to draw points, lines, and circles, that is, compass and straight edge constructions. Analytic geometry is sometimes called Cartesian geometry or coordinate geometry, and it's the study of shape drawn on a coordinate system. Measurement, which is closely aligned with analytic geometry, is used to signify the study of quantity when it's applied to 1, 2, and 3-dimensional geometric objects using common units. So length, area, and volume are examples of measurement topics in K-12 geometry. Transformational geometry is the study then of shape understood according to the size and shape preserving actions of reflection, rotation, and translation. So mirrors, turns, and slides, sometimes called those three things, as well as the shape preserving action of dilation, which is enlargement or reduction. So sort of movement geometry. And then here's my statement about the three geometries in problem solving. I think when students are presented with authentic problem solving settings, the three geometries serve as resources in the problem solving process. They're tools, right? Tools that kids access when they try to solve geometry problems. And while some problem solving prompts require the application of mathematical tools from only one of the three geometries we've explored, it's perhaps more common that two or more perspectives are helpful in the construction of a solution. This is the hard part, I think, about teaching geometry and helping kids problem solve geometrically, is that we have these different perspectives, and usually more than one perspective comes into play when we have to solve a problem. So in other words, they're used in sort of a combined effort or a combined effect on problem solving prompts to arrive at a solution. And I know no way to help kids get used to that other than to give them lots of opportunities for problem solving. I have some examples, and I chose to draw my examples all from the middle school math competition that's called Math Counts. If you're not familiar with Math Counts, I guess you'll become a little familiar through these problems. But it's a really it's what I would think of as one of the best math competitions in the United States. It's really well written. The problems themselves are really original and tend to all fall straight into this category of problem solving. Very few of them are algorithmic type of questions you might call an exercise. Almost all of them require the student to think originally and to really engage in authentic problem solving. So I think you'll see that as we go through these. Your exercises this week are all drawn from Math Counts as well, as is the problem solving prompt. If you want, you're given the choice to choose a problem of your choosing for the last problem solving activity this week. But Math Counts, I have a library of Math Counts questions that you're sure welcome to draw from. Okay, well, I guess we could go ahead and get started. Let's take a look at the first example. So this is example one. Some of these questions have a number next to them, and that's just, I couldn't get rid of the number off of the copy I made from the actual test. So ignore the 17 there. It says a square has sides of length 4 units each. A stripe of width 1 unit is drawn inside the square, centered on the diagonal. The area of this stripe can be expressed in the form a plus b times the square root of 2 square units, where a and b are rational numbers. What's the value of a plus b? Express your answer as a decimal to the nearest tenth. All right, so we have this picture drawn. Let's go ahead and switch over to my Elmo cam. There it goes. All right, so it's a picture something like this, and we're told then that this is a square, so we can think of this as right angles, 4 units on a side, and we have something here drawn in the middle, or strip drawn in the middle, and we're told that that's just 1 unit wide, and that the strip is centered along this diagonal. So right away we're sort of thinking of this as something that's symmetric. So right angles everywhere here, just adding to the drawing at this point. And the question is, you know, this guy's area, we're told, can be written as A. Let me just make sure I have it here. I think I had it. Yeah, A plus B times the square root of 2. So A plus B times the square root of 2. And what do we want to know? We want to know what A plus B is. And we can write it as a decimal, rounded to the nearest tenth, it said. So it seems like an authentic problem-solving setting. I mean, I have no algorithmic way of producing an answer here. This is no templated problem that I've ever seen from a high school textbook or a middle school textbook. And so the big question is, well, how do I get at A plus B? So a bunch of different ways that we could go about this, right? One thing that I notice is that there is a line of symmetry here, right, that we could take advantage of, and let's just go ahead and try it that way first. So let's go ahead and draw this thing, sort of the half picture of it. So I'll go ahead and draw this in. Rough sketch. Looks something like that on the half picture. So if this distance here is 4, and this distance here is also 4. And let's see, so let's think about this. If this is along the diagonal and this is a 4 by 4, then these are both 45-degree angles. This is, I guess, we would call this an isosceles right triangle. So that means that this is, you know, a 45, and so is this, and so is this. We're also told that this distance here, well, it was 1 there, so that must be by symmetry that this distance right here is equal to half, right? One thing that I notice is, you know, that well, if we want to find the area of this inner stripe, it would just be double the area of this half stripe. So if I could find the area of the half stripe, then we're in good shape, right? And when I look at the half stripe, to me, the shape appears to be, these two lines are parallel, so to me it appears to be a trapezoid. And we know that the trapezoid's area is equal to, let's see, 1/2, what would it be, base 1 plus base 2 times height. Of those things, we know a few. Well, I guess we only know one from the drawing, and it's this height, right? The height itself, we're told, is that distance right there. It's half. It's the distance that separates the two bases. But we could probably figure out what these two bases are if we could somehow find out, I guess, how much the 4 has been shortened in I guess, painting the stripe down the middle. The problem is we know this distance, we don't know that distance right there, which sort of leads me to this idea that, well, what I really need to do is solve a little triangle right in here. So I'll draw it in right in here, and then what I'll do is I'll enlarge it down here and draw it larger. So the larger drawn triangle, exploded view, I guess. Oops, I drew it wrong way. It would look something like this. So let's see, something like, just trying to think how to draw it best, something like that, I guess. So we know that this angle here, I'm going to call right angle because I'm chopping it right there. This is a 45, and we know that that distance is 1/2, and we know that's a right angle, so that makes this one also a 45. So again, I have an isosceles right triangle, which makes this a half right here. And the question is what's this distance? If we can find that distance, then what we can do is we can find what this distance would be, right? Once we know that distance, which will be the same as this distance, we can find the area of this triangle and take it away from the area of the larger triangle, which will give me the area of the stripe. Okay, so I think I have a plan forming here. So let's call this little distance in here, I don't know, let's call it distance D. So I'll call it D. And of course, this is a right triangle, so I can use Pythagoras. So what do I have? I've got D squared is going to be equal to 1/2 squared plus 1/2 squared. So D squared is equal to, there's two 1/2 squared, so those are 2/4. So D squared is equal to 1/2 itself. So that means D must be the square root of 1/2. Same thing as 1 over the square root of 2. We could rationalize the denominator if we wanted to, root 2 over 2, so multiplying by a smart form of 1 there. So we end up with D equal to root 2 over 2. And now I always like check things with a calculator just to see if they make sense to me. Square root of 2 divided by 2 turns out to be about 0.707. Which makes sense, right? The hypotenuse has got to be longer than either of the two legs in a right triangle, and it is indeed longer. So 0.707 is what we get for a D there, which makes it possible then for us to find this distance here. So here's my D, and this distance here would be 4 minus D. All right. So let's see, the distance 4 minus D is going to be equal to 4 minus root 2 over 2. Okay, so that's basically the leg of the triangle here, the one that I'll sort of shade in. And that allows me to find the area of that triangle. And I'll easily be able to find the area of the large triangle. Like, it's 4 times 4 divided by 2, so the area of the larger triangle is 8. So I need to take this area away from 8 to find the area of the stripe. Turns out I'm kind of going away from using the area of the trapezoid, the thing I was thinking about at first. But let's go ahead and try that. Let's see, so let's find the area of the small triangle. So I don't know, maybe we should put some letters in here. Let's call this this point here A, this point B, and this point C. Let's call this point D, and let's call this point D, E. So I'm trying to find the area of DEC. So the area of triangle DEC is going to be 1/2 the base times the height which is 1/2. We know both base and height are this number, 4 minus root 2 over 2. Oh, this is gnarly, huh? So it turns out that we're going to have to use a double distribution here to simplify that area. I get 1/2 times 16. 4 divided by 2 is 2, so it'll be minus 2 root 2 minus 2 root 2, and then root 2 times root 2 is just going to be 2. It's going to be positive. 2 times 2 is 4, so I'll have a half there. So let's see, what do I get? I get 1/2, 16 plus a half, so it's 16 and a half. And then minus 2 root 2 twice, so that'd be minus 4 root 2. And then I'm supposed to multiply that all by half. I'm going to rationalize, or I should say, right, this is an improper fraction, so it'll be 33 halves. Which is 33 fourths minus 2 root 2. So I mean, again, I would probably check this on a calculator, make sure I've done some. So 33 fourths, I haven't done something in error, minus 2 times the square root of 2. I'm getting 5.42. I don't know. Which seems to make sense if I kind of go back to my drawing. We know this distance is 4 and this distance is 4. So the area of the big triangle is 4 times 4 divided by 2. So 16 divided by 2 would be 8. And the shaded triangle, DEC, we're getting somewhere in the neighborhood of 5.5. So in other words, we've lost about, I don't know, 2.5 units right here, which means that the whole thing should be around 5-ish. Let's find out. So let's see, we know that the area of triangle ABC is equal to 1/2 base times height. And here I get, what, 1/2, 4 times 4. So half of 16, or 8. And that means then that the area in my drawing, it's going to be what, ABDE. It's the trapezoid. That's going to be the area of the big triangle minus the area of the smaller triangle So I guess if we were to do an exact number, it would be 8 minus 33 fourths minus 2 root 2. So let's see, if I wanted to put this over 4, it would be what, 32 fourths, right? I'd be taking away 33 fourths, and then subtracting the negative would be adding 2 root 2. So we end up with 2 root 2 minus 1/4 as, I guess, the area of the trapezoid. I mean, if we sort of hit this on our calculator, 2 times the square root, sorry, I'm a little off the screen, I'm just realizing, 2 times the square root of 2 minus 1 divided by 4. Yeah, I get somewhere in the neighborhood of 2.5, which is about what we thought, right? We could have just, I guess, subtracted these two as a decimal, since our answer only needs to be a decimal. But let's go ahead and finish it out using exact numbers, 5, 7, 8-ish. So that's the area of the trapezoid here, right? But what I want is the area of this whole stripe, which is double the area of that trapezoid. So I'll just write that down next. The area of the, call it the stripe, is equal to 2 times the area of ABDE, which is just going to be 2 times that, what, 2 root 2 minus a quarter, which is going to end up as, what, 4 root 2 minus a half, which as a decimal, of course, will just be double this number, which is 156, and I can't remember the units, but I think it's just in regular units. But keep in mind that what they asked for was a plus b square root of 2, right? And they want to know a plus b. That's this interesting, way to ask for an answer. I'd be curious why they want the answer in this form. Obviously, if you can find the area, you can find a plus b. So let's see here. The a in this case, so a in this case is going to be negative 1/2. B in this case is 4, and we're just supposed to add a plus b. So a plus b is what, negative 1/2 plus a 4. So it's going to be 3.5 is our answer, written to the nearest tenth. So there it is, a first example of, I guess, problem solving, and it's kind of interesting to think about, to go back and think about how the different perspectives work in here. So, I mean, if I just even start, I mean, it's obviously a measurement problem right from off the bat, right? Because we're talking about area here. So there's definitely some measurement. You have to understand measurement to even get off the ground. I instantly used a transformational geometry strategy where I noticed that there was some symmetry, that this had twofold symmetry, and that perhaps it's easier to just think about half of the problem and doubling it. So I brought into play transformational symmetry. And then to me, it seems like there's a lot of analytic geometry going on here, right? We're choosing points and creating new triangles, analyzing those triangles using Pythagorean theorem, something that we often use to find distances that are unknown. So definitely some analytic geometry, although we never did really put it on a coordinate plane. That would have been an interesting strategy. I didn't even consider that. And then we're sort of back to measurement here, sort of using addition and subtraction of areas, chopping the figure up and saying, well, if I want to know this stripe, which is kind of hard to calculate because I'd need to calculate both of these bases, maybe the easier way to do this would be, to think of it as a big triangle minus a smaller triangle to find out what's left. So sort of this additivity principle of area is what's going on there. And then in the end, we get an answer, but then we have to interpret the answer for the test writer's, a plus b part. Okay, well, this is kind of an interesting one to start with. Example 1. Quite a bit of different perspectives at play in that first example, I think. Let's take a look at another one. So here's a second example. Circle O has radius 10 units. Point P is on radius OQ, and OP is 6 units. How many different chords containing P, including the diameter, have integer lengths? So this is kind of interesting problem. I can see that by virtue of the fact that it's problem 22, it's one of the harder problems from math counts. This is from the sprint round, which is the first competition. It's 30 problems in 45 minutes, and the problems get progressively harder. So once you get into the 20s, the problems get a little bit more complex and hard. So let's read it one more time. Circle O, radius 10 units. So that means OQ is 10, right? And point P is on radius OQ, and OP itself is 6. How many different chords containing P, including the diameter, have integer lengths? All right, let's think this one through. Bring up my MoCam again. All right. Well, let's draw a circle to begin with, get a good picture here going. Let's go ahead and draw in this O and P. I think it's sort of right here-ish. This is P. And I think this was called Q. And then the question was, well, how many different chords through P have integer lengths, right? So it's a really interesting question. You know, we can draw a whole bunch of chords through here, right? And think about them. Probably should draw this one. All these things. So these would all be different chords drawn through P. And we're supposed to also include the diameter, have integer lengths. Okay. So just by sort of looking at the drawing, it seems like we have sort of long chords, longer chords, or shorter chords, shorter chords, shorter chords. And when we're perpendicular to the diameter, it appears that that's the shortest chord just by inspection. And then as sort of this end's short and this one's lengthened, and it seems like they get longer again. So it appears that all the chords are, I guess, you know, shorter or equal to a diameter of the circle. So right away we sort of have a sense of the maximum, right? Let's fill in some distances here. We know that O to P is 6, and we know that the radius of the circle is 10, right? Yeah, so that makes P to Q 4. That would mean if I sort of OPQ, let's call this R, so then O to R would also be 10 here. So some observations we can make just from the drawing. Let's see, let's call it RQ is the longest chord. At 20 units. So we know that's as long as it can get. The big question is how short can it get? Let's go ahead and put a point on this one. We think that this one that's perpendicular here, right, is as short as it can get. Just by looking at the drawing, I probably should prove that, but I'm going to just assume it at this point just by inspection. It appears that that's the shortest one. And the question is, how long is that one? Let's see. So let's give that point a name right here. I guess, I don't know, QR. Let's call it SS prime. SS prime appears to be the shortest chord. And the big question is, how could I find its length? And it looks like we have a right triangle that we could draw in there, right? So there's a right triangle in there that I could solve. And the big question is, how could I solve that with only one side? but I recognize, oh wait, that's a radius, right? O to S is a radius, and we know the radius of this circle is 10, so OS is 10. So that means that SP squared plus 6 has got to be equal to 10 squared. So we get SP squared equal to what, 100 minus 36, which is of course 64, which square root is 8. Oh, that makes sense, right? Because this is just a 3, 4, 5 triangle that's been scaled by a factor of 2. So that distance would be 8. Now by symmetry, this would still be 10 and this would still be 6. So this distance here would also be 8. So that means that this chord SS at prime is 16. Okay, so we know sort of the maximum and we know the minimum, 12 and 16. And the question is, what about the ones in between? And if we just sort of think about, this sort of chord rotating, it seems that it's growing continuously as we move it to this direction, right? And max is there, and then it sort of shortens, shortens, and minimizes there. So it appears that you would go through every single example, I guess, of a length as you get longer and shorter, right? So I guess the next observation would be every integer length between 16 and 20 is available as the chord lengthens continuously via rotation. About P. So that means that that is, let's see, what, 17, 18, and 19 should be lengths of chords here. And so at first glance, and I'd be really curious to see the distribution of answers on this one. At first glance, it appears that 16 and 20 are both available, as are 17, 18, and 19, right? So to me, it seems like 16, 17, 18, 19, 20, there should be 5 chords of integer side length here, at least at first glance. But one of the things that I've noticed about this problem is that anytime you get a chord that's sort of in between 16 and 20, let's say this one right here, let's say that this one right here was 19. Let's just sort of highlight it. Say, if this one was 19, that we could repeat 19 just by symmetry on the other side. In other words, if I sort of just drew one more in here as an example, something like that-ish. It's a little bit off, but so if we sort of rotate the 20 chord just a little bit smaller, we get 19. But reflecting that across the line RQ, we would get another chord on top there that's also 19. So I would say that the last observation I'm going to make is that each of I'm going to call them in-between chords, that is 17, 18, and 19, are doubled via reflection across ACRO, across, what is it, RQ. So what does that mean? So that means that instead of 5, there's 3 more, there's 8, right? So let's just summarize. There are, let's see, one chord of length 16, sorry, one chord of length 20, and there are two chords of length 17, two chords of length 18, and two chords of length 19. And I'm pretty sure that's all of them, or at least that would be my answer at this point. 17, 18, and 19 are all doubled, so 6, 7, 8. So total of 8 chords of integer length. Let's stand back and look at this thing a little bit. One thing I thought also was neat about this is that you have to be careful, right? The reason that RQ, the one of length 20, doesn't get doubled is because it is actually the line of reflection, and when you're reflecting across a line, every point on the line is fixed. So in other words, it's itself via reflection. And the reason that 16 chord doesn't get doubled, and here I'll draw it in blue, is because it's perpendicular, right, to the line of reflection, which is the orange line here, so it reflects onto itself. And again, it's the same line, right, so we wouldn't count it twice. But these ones that are in between, of course, the ones like 19, we're just sort of assuming this one is 19, would be, I guess, doubled each time. So yeah, again, 17, 18, and 19 all doubled. So let's stand back and think about how the three perspectives, come into play here. I mean, it's pretty obvious that this one is really rich in perspectives. I mean, you really have to think about reflection in order not to miss observation number 4. You have to also use reflection to be able to sort of assume that if this is 8, that's 8. So we're thinking about transformationally there. Certainly this move is, we're finding an unknown distance, so we've applied a metric space, or a distance, I guess, unit to the figure. Anytime distance has been imposed on a figure, you're either in measurement or analytic geometry, so we're definitely measuring here. The only one that doesn't really come up for me too heavily here is, I guess, synthetic geometry. We haven't really proved anything using, for example, a minimal condition for triangle congruence. So it seems like this one's pretty heavy on measurement and transformation. All right, I'll put that aside. Let's go do one more of these. It says square ABCD is inscribed in a circle with diameter BD of length 2 units. Segment AB is the diameter of the half circle on top of the square. What's the area of the shaded region in square units? Express your answer as a common fraction. Area of the shaded region in square units. Express your answer as a common fraction. Okay, so let's just sort of digest the picture. We've got a square inscribed in the circle, and then we've got a half circle or semicircle on top of the square. So from A to B is really a semicircle up on top. And what we're kind of doing is taking the piece of the circle out of the half circle to find the area of the half circle, and it should be a common fraction, which is kind of interesting. In other words, the area of that shaded section is not irrational, it's rational. And perhaps that has to do with the fact that, I don't know, we have some sort of a, we'll find out. We'll find out how that has to do, what that has to do with. Okay, so we need a picture of this first. So let's switch over to the Elmo cam. So here's a picture, I guess, of what we have. We know that this distance is 2, and of course that's a diameter, and so this is 1 and this is 1, and and that this thing is a square, so we know that all the sides are the same, right? Um, and what we're trying to find out is I guess the area of this region. Um, let's call this A. Um, and you know, at first it doesn't appear like there's enough information given, but if we kind of think about it, we can start ticking away at it. I know that this is a right triangle because this is a square, and I know that these are the same, right? Because this is a square. So that means that, you know, x squared plus x squared has to be equal to 2 squared here. We could find what the side length of the square is, and then I could, well, that's, you know, I could, I know what the area of the, then I would know what the area of the square is. I could subtract the area of the square then from the area of the circle, and that would allow me to find the area of these regions right here, right? So let's call this, um, I don't know, we'll call this area 1, we'll call this area 2, area 2, area 2, area 2. And if I could find, you know, if I know, I guess, the side length of the square, I could find what the area of the half circle built on the side is. Um, and if I know the side length of the square and I know the radius of this circle, I could subtract the square from the area of the circle and divide the remaining area by 4 to find what these four area 2's are. And then I could subtract area 2 from the area of the semicircle to find area 1, it seems like. So that's my plan, roughly. I guess the first thing I'll go after is the side length of the square. So the side length of the square is something that looks like, oh, bad drawing. Something that looks like this. We know these are the same, and this is 2, so we'll call these x's. So what do we have? We have x squared plus x squared equals 2 squared. So 2x squared equals, what, 4? Divided by 2, and I get x squared equals 2. So that means x has got to be root 2. So that means the length of the side of the square is root 2. So, you know, rough picture of that is sort of like this. Root 2, root 2. So that means the area of the square is going to be root 2 times root 2, which is just 2. So the area of the square is 2. And let's see, I've got the area of the circle, which is just radius 1, right? So the area of the circle is going to be pi times 1 squared, or just pi. So that, now that I know the area of the circle and the area of the square, I should be able to find area 2. So let's find that. So area 2 is going to be 1/4 the area of the circle minus the area of the square. The reason I say 1/4, of course, is because each one of these combined together makes the total, you know, subtraction of the area of the circle minus the area of the square. So let's try that. Let's see, 1/4. The area of the circle is pi. The area of the square is 2. So it's pi over 4 minus 1/2. And that's what a sub 2 is. Okay. So now I just need to know what the total area of the semicircle is. That is what area 1 plus area 2. So let's call it the area of the semicircle, or half circle if you'd like. That's, you know, area 2 plus area 1. But it's also equal to pi times r squared, where r is the radius here. And since it's a semicircle, that radius is, you know, it's this, it's that distance, right? Which is just half since that distance has to be repeated over here, it's got to be half the side length of the square, and the side length of the square is square root of 2. So that means that we take pi times square root of 2 over 2, and we square that thing. And let's see, what do we get? We get pi times, let's see, 2 over 4. So that's going to be pi over 2, right? Oh, but I got to be a little bit careful here, right? Because it's a semicircle. It's not a full circle. I was just looking at my notes and I caught a mistake. It should actually be a half, right? Because we're only doing a half circle. I wonder if you caught that as you were watching. So that means that this is actually pi over 4. Okay, so I get pi over 4 for the area of the full semicircle and the area of, so I guess we now can solve for area 1. Now I'll just call it a sub 1 since I've already got it labeled. Area 1. Area 1 is going to be the area of the semicircle minus a sub 2, right? So the area semicircle minus a sub 2. We're told the area of the semicircle is pi over 4. And we're taking away a sub 2, which is up here as, oops, I'm going off the page, I'm sorry. I have to keep myself reminding myself. So area of the semicircle minus a sub 2, again, here's the semicircle, there's a sub 2, I want a sub 1. So you take away a sub 2 is pi over 4 minus 1 half. And interestingly enough, the pi over 4's cancel, and we just get 1 half. And that is our answer, I guess, in units squared, right? And it does lead me to believe that we found the right one, because it says write your answer as a common fraction, which certainly that's a common fraction, so it's rational. And I think what's kind of interesting here is that it had an irrational radius, and I think that's what somehow opens the door for a rational area here. You would think, looking at this curved region, that we'd probably get some sort of a multiple of pi or something, especially given the fact that the radius of this circle is rational, right? But kind of an interesting case here, since this one has a rational radius. Its side length will be irrational because of the square root in Pythagoras. Since the side length is irrational, half the side length is irrational, meaning that this particular circle has an irrational radius. And that irrational radius, there it is, gets squared out. Although, we still have the pi in there. It's interesting. I might have to think about that a little bit more, about what are the conditions by which that area always results in a common fraction. Anyway, think about that a little more. If you have ideas, let me know. But I think that another really good example here of problem solving in a K-12 setting, a middle school, a math competition, a problem that really relies on a bunch of different perspectives. And let's just sort of recount our perspectives here. So, one of the things right away I took advantage of was symmetry. This diagonal itself is a line of symmetry for the inner circle, meaning that I don't have to solve both triangles to find out that particular radius. What I just need to do is solve one of the triangles for a side length, and by symmetry that'll be the side length for the whole square. And then I used certainly some measurement and analytic geometry, first to find a missing side length of a square, and then also to find, I guess, areas of circles and squares that allowed me to subtract the square from the area of the circle to find what these little, we call them lunes. These little lunes are pieces of circles that are created by chords. And once I knew what the four loons were, and again, I was, applying symmetry here. I was thinking to myself, well, once I know one, I really know all four. And in fact, I can use that in this calculation of 1/4. So again, appealing to symmetry of the figure. So some transformational geometry there allowed me to figure out what a sub 2 was, these little loons. Once I knew what a sub 2 was, and once I knew the area of the semicircle, then I could subtract a sub 2 from the area of the semicircle to find out what the shaded area was. So there I'm using an additivity of area. So again, thinking in terms of, I guess, measurement and the additivity principle in measurement, and finding the area of an unknown, you know, region that's going to be really hard to calculate analytically by just recognizing it as the difference of two known regions that were easier to get at analytically. So again, I think it's really strong example of transformation and analytic and measurement perspectives on geometry. Again, not a ton of synthetic geometry here. I didn't really prove something. So there it is, the third example. Let's put that away. And let's just do a little bit more time here. I'm nearing in on an hour and hoping to end shortly. But, problem solving in geometry is a complex process. I'm sure, watching me problem solve on tape, even with a script sitting next to me, it's still hard for me to do. And it's really not easily understood without graphical support. So in all of these cases, I drew a picture, and I'm really careful about drawing pictures when I do problem solving because I want the picture to help me. I want it to, I guess, give me intuition. And I will say that, often when I get a geometric problem solving setting, the first thing I do is go to GeoGebra because I know that GeoGebra will give me an absolute perfect picture, and that the picture will not, I guess, distract me, or, lead me astray by some, I guess, sketching error. It'll actually be as close as it can be to the actual thing, the actual problem solving setting. So I guess I'm making the point here that GeoGebra is an ideal tool that can be used to encourage problem solving by providing scaffolding applets that students can use for support when they don't know what to do. So I guess the thing I want to teach you today is how can you make an applet with GeoGebra? Sometimes giving the kids the full tool and asking them to construct a picture is just too much. It might be, take too much time for 20 kids to draw the same picture. But one thing that you can use GeoGebra to do is you can create the picture, and then you can upload it to a space in the cloud that GeoGebra provides for free to share with your students via a, a, a simple web link. So that's kind of the last thing I want you to learn how to do in GeoGebra, and I hope that maybe you will use it with your students to share complex pictures or anything that you could create that might support their learning. So let's take a look at this and using one of the previous problems as an example, and imagine that you've assigned the problem to your class and no one's able to get started. So rather than showing them how to do it, you decide to give them some support in the form of an applet that they can explore to support their idea generation. So I hope that gives you, oftentimes with problem solving, kids just have a hard time getting off the ground. I don't know what to do, right? They've been oftentimes taught mathematics in a way where the example problem tells them what to do, and of course problem solving by definition has no example problem. It's, one of my colleagues used to say that problem solving is what you do when you don't know what to do. So how do you get kids started in that practice? And one thing I've found that's really helpful is to give them rich pictures that they can interact with and talk about and help them get started. So let's do that second problem as an example here. So I'm going to bring up GeoGebra, and what I'm going to do is the second problem, which is the one about the circle chord lengths. In this particular setting, I don't think I really need the X and Y axis, so I'm going to turn those off. But I do need a circle with a center and a certain given radius. So what I'm going to do is actually use the circle with center and radius tool. I'm going to put a circle in here, and its radius is 10. So there it is. There's the circle with radius 10. I'm going to zoom in a little bit so that it's not so big. Oops. Of course, now it doesn't cancel that. And then we need a chord, or I should say a diameter, or excuse me, a radius. I can't even think here. I want that radius. And then we want a point on this radius that's 6 units from the center. So I'm actually going to use the circle with center and radius again, and do one with a radius of 6, and then find that point of intersection. There it is. And then I'm going to hide that second circle. What that does is it gives a point on there that can't be moved. Since I'm building an applet, and that's one thing I don't want to move, I built it that way. You know, the center is still a point that can be moved, and the radius is still a point that I guess could be moved here. But yeah, so I guess a couple different things we could do. I kind of don't want that this thing to move, because what I want to move is the chord. And so what I'm going to do is I'm going to hide this one. That's point B. And I'm going to put a new point in there that's at the intersection of the two. There we go. That one's not going to move. And then I'm going to hide this point A. There we go. And well, maybe I'll just leave A. I guess it really doesn't matter if a student interacting with the applet moves that point, does it? Probably not. Oh, anyway, I'm just thinking out loud. So there it is. Now what we want is we want a chord. So a chord, of course, is any line that intersects a circle. And this particular chord we want to intersect with that point C. So what I'll do is I'll use a line, and I'll first put a point on the circle, and then I'll construct a line through that point, and then I'll find the point opposite there. And then what I'm going to do is I'm going to hide this line, and then I have my chord, which I can draw in as a segment now. And that segment has one piece on it, right, that changes. And I think that's the picture we want to share with students. But really what we want them to see is sort of the length of that segment. So let's go ahead and get that length of that segment. I mean, we actually have it here. It's 17.77 right there. There it is. So let's go ahead and I don't know, I guess we could put in the distance here, right? So distance or length would be boom, boom, FE, there it is. And then I think we need to make sure that we have the picture labeled similarly to what we had in the setting. Let's go back and take a quick look at it. O, P, and Q are the points here. So this guy I'll call O. So I'm just clicking on the point and then just typing the new name, P, and this guy is Q. There it is. I don't know, something like that. Since it's going to be an applet and those are relatively small, I'm going to make my font size a little bit bigger. How about 28 points? There we go. Zoom in a little bit. There it is, O, P, and Q. What might be kind of fun would be to include a text box with dynamic text. I'm going to put a text box in here that says FE is equal to, and that was the number over here, H. So it's an object already. I could put it as text FE, but yeah, that's good. That'll work. Put that off to the side. And now if I grab E, rotate it around, maybe. Oh, there we go. Grab E and rotate it around. I can see that, yeah, indeed 16 is one of my lengths, and it looks like 17 would be one of my lengths in here. I could probably find it. There it is. There's 17. Um, but I could probably also find 17 down here, right? It's the reflected version of the one I did. There it is, 17. So, so it seems like our reflected idea is definitely shown here. And of course, this one's going to be 20. Let's see if we can find 19 and 18. There'd be 19 is going to be somewhere right in here. Really hard to get it right on, but there it went. There's 19. And then let's see, 18 is going to be right in here. There's 18. Of course, there'd be two of those. Reflect that across the diameter. And then we already saw 17 and 16 is right there. So it seems like I guess, our theory seems to be proven out by GeoGebra. At this point, I think what I'd do is get this thing ready for export as an applet. Maybe something we could you can put text on the applet here, or you also have opportunity to put text above and below the applet when we upload. So I think I'm going to leave the instructions to the upload and do it here. Now, one kind of cool thing you might want to do is make this an animatable point, a point that moves along the circle by itself. So there it is. That's an animation button you can add, and this little controller in the lower left-hand corner will, of course, start and stop it. So I kind of like the animation. Kids seem to really love animating objects. I've seen them do some amazing animations just because it's fun to watch the thing move. So there it is. I think I'm about ready to export. I'm going to get rid of the grid. I think the grid distracts at this point, so I'm going to get rid of it. I think I'm actually going to hide this now. I'm going to get this text out of the way. That's really just a question about what you think you'd prefer. And there it is. I think we're ready to export. I'm going to move this a little bit off, move this a little bit off. I often get rid of the algebra view, this piece right here. And then one of the things I like to do is make this, oops. So to make the screen as small as possible, because whatever the screen becomes, the size of the screen becomes the size of the applet. So I usually make the screen sort of about 75%. I mean, you don't want it so small that you can't really interact with it. Move it into, get rid of white space is, I guess, what I'm doing here. I'll move this back over. That seems to be like it would be acceptable for a size of an applet. So the idea is that the applet's going to appear inside somebody's browser, and the browser is going to have a heading across it and sort of scroll bars on the left and right, and probably something along the bottom. And so it'll sort of scrunch down whatever the applet is. If the applet's full screen, you'll only see part of it. So if you make the canvas sort of about smaller than full screen, if you cut it down to at least 75% of height and width, then it usually fits in the applet view fairly easily. Now, I'm already signed in because I have an account in GeoGebra, but if you don't have an account in GeoGebra, you can go ahead and sign in here, and it'll ask you to give them an email and set up a password. But what that does is basically gives you a place in the cloud that GeoGebra provides for free to post and share your drawings. And so the way you do that is you just go to File, Export, and its web page, and I'll go ahead and do that now. If you're not signed in at this point, it'll prompt you, to set up an account. So the title is, let's see, I'll say M573 problem on circle chords. Text above the construction or text below the construction, so you can put text above and below. And I'll just put how many chords are, oh, you know, one thing I just realized, I'm sitting here thinking, did I remember everything? You know, I didn't put in this distance here or this distance there, so let's put that distance in really quick. Oops. So let's see, OP is 6. Let's see, can I move that? Yep. And let's see, this number 10 is, and let's see, distance or length. PQ is 4. This 10 I don't like. Show label there, the 10 is away now. This would be interesting to put, it might be better to have might have been better to put it over here, but I don't think it's too bad. Sort of gets in the way, doesn't it? Yeah, let's put it off to the side. OP equals 6, and then what is it? PQ equal 4. So we can leave that off to the side. And I'm going to go ahead and just get rid of these distances. Delete that, so that the drawing sort of speaks for itself. Okay, I like that better. Okay, sorry. Now let's go ahead and edit or export to a web page. And the question is, how many chords of integer length pass through P? I think that was the way it was put in the... How many different chords containing P, including the diameter, have integer lengths? Maybe we should just write that. How many different chords containing P, including the diameter, have integer lengths? And of course, if you want to put something below, what I probably put is some invitation, drag point E to investigate. And I think that's what I want. This is preparing to upload, and then I'm getting my, this is what GeoGebra, it'll fire up your internet browser, and you'll get a preview. This is the preview of your applet. What I tell you to do is to make sure everything's working the way it should. You can see that the player is still there, and you can see why now I got rid of the algebra view. I really don't want the algebra view off to the side. I just want kids to interact with the object. And drag point V to investigate. We go ahead and save and close it, and it's saved. And so now you can go to your own, this is my own page in GeoGebra, and I can see that it's one of the available resources, and it can be shared with a link. Here's what it looks like right now, and you can see that it is actually a little bit oversized. It comes up pretty big, so that advice to you to make the canvas as small as possible before uploading might be, you know, I probably should have made it about that size, a little bit smaller, but it seems like it still works pretty good. And you can still animate it here if we want to, and watch those, what were they, 8 different lengths show up. Okay, I hope that gives you an idea on how to share resources created in GeoGebra with your students or with other teachers, and use that powerful tool, I guess, to help kids visualize problem-solving settings, and perhaps create more, you know, help them get off the ground when they're stuck and don't know what to do. Well, that's really about all I have for today. That's the end of my slides, and I wish you luck in this last week of course, and do let me know if you have any questions about any of this material. I'll talk to you soon.